In this video, we'll discuss the response of an electron to a magnetic field. We'll start by discussing the Hamiltonian of the electron in the magnetic field. Then we'll look at the response, time-dependent response, of the magnetic dipole at rest. And finally, we'll talk about Larmor precession. So, orbital angular momentum implies a circulating charge for an electron in a hydrogen atom, for example. That orbiting charge, or circulating charge, leads to a magnetic moment. Similarly, because spin behaves just like orbital angular momentum, it must also be associated with a magnetic dipole moment. We can write that moment, mu is equal to gamma s, where s is the spin matrix, and so this is now an operator, magnetic dipole operator. And gamma is called the gyromagnetic ratio, which is a multiplicative factor. In the presence of a magnetic field, this dipole will feel a torque. Tau is equal to mu cross b, where b is the magnetic field. And the energy of this system will also depend on the magnetic field, and it's given by minus mu dot b. That means that we can write the Hamiltonian for a particle with spin in the presence of magnetic field as h is equal to minus gamma b dot s. So this is an operator, this is an operator, and these are constants. If you have a particle with spin 1/2 at rest in the presence of magnetic field, and the magnetic field is in the z direction, we can write that magnetic field as B is equal to B sub 0 times the unit vector in the z direction. The Hamiltonian, therefore, is given by minus gamma B sub 0, and then we had B dot S, which pulls out the z component of the spin matrix. Well, we know what that spin component is. It's h bar over 2, 1, 0, 0 minus 1. And so this gives the Hamiltonian the same matrix times minus gamma b sub 0. The eigenstates of this system are exactly the eigenstates of s sub z, because all this is a multiplicative factor times s sub z, with eigenvalues e plus and e minus. So the spinner up, gives you E plus, and the energy is minus gamma B sub 0 h bar over 2, and that's when the spin is aligned in the same direction as the magnetic field. The dipole moment is aligned in the same direction as the magnetic field. And then you have the spinner down, gives you E minus, whose energy is plus gamma B sub 0 h bar over 2. So when you have the magnetic dipole aligned along the magnetic field, your energy is lowered. When the magnetic dipole is aligned opposite to the magnetic field, the energy is raised. The time-dependent Schrödinger equation is now simply given by IH bar d chi by dt equals the Hamiltonian applied to chi. And we can solve this in terms of stationary states of the Hamiltonian, because if we know the energy, we know what the time-dependent part of this equation is, the solution. And we can then write it like this. Chi of t is equal to some constant times the spin-up state times e to the minus I e plus t over h bar with the time dependence, plus b times the chi down state, the spin down state, e to the minus I e minus t over h bar. And that's simply a vector, one element being a e to the I gamma b sub 0 t over 2, and then the second element being b e to the minus I gamma b sub 0 t over 2, when we substitute in e plus and e minus. The constants, a and b, are determined by the initial conditions. So at time equals 0, the spin state is given by AB, a vector AB. Assuming that a squared plus b squared is equal to 1, we can suggest that a good way of writing this would be to parameterize a and b in terms of an angle alpha. So we can write a is equal to cosine of alpha over 2, and b is equal to sine of alpha over 2. So then we take a squared plus b squared, we just have cosine squared plus sine squared, which is always equal to 1. Therefore, we can write the time-dependent solution in the following way. Chi of t is cosine of alpha over 2, e to the I gamma b sub 0 t over 2. And then the second component is sine of alpha over 2, e to the minus I gamma b sub 0 t over 2. The expectation value of the spin as a function of time, the spin operator as a function of time, can now be calculated by applying the spin operator to this state as a function of time. So we'll first start with the Sx component, because we have to do Sx, Sy, and Sc. So what is the expectation value of Sx? Well, that's chi dagger of t, Sx, chi of t. We know what chi is, we know what chi dagger is, because that's just the transpose. So chi dagger is a row vector with the first element being cosine alpha over 2 e to the minus I gamma b sub 0 t over 2. Notice that we flipped the sign on the I for the complex conjugate. And the second element is sine of alpha over 2 e to the plus I gamma b sub 0 t over 2. Then we have our spin matrix S sub x, which is h bar over 2, 0, 1, 1, 0. And over here we have chi of t, just like up here. We can now apply this matrix to this vector, and then take the inner product of the resulting vectors. Well, that first application, we pull the h bar over 2 out here. We still have our row vector, and now we have a column vector from this, which gives us sine at the top and cosine at the bottom. So it's sine alpha over 2 e to the minus I gamma b sub 0 t over 2, and then the lower term is cosine of alpha over 2 e to the I gamma b sub 0 t over 2. When we now take the inner product of these two matrices, which should give us a scalar, these two vectors will give us a scalar, it's going to be cosine times sine and sine times cosine. And you'll notice that the signs of the exponential are the same for both these terms, and this term have the same. So we get h bar over 2, cosine of alpha over 2, sine of alpha over 2, and then we have e to the I minus I gamma b sub 0 t, because we have two of these. We get rid of the 2 in the denominator there, plus e to the I gamma b sub 0 t. Again, these two give us a removal of the 2. Well, this, we're all familiar with this. This is just equal to a cosine of gamma b sub 0 t. But more than that, this is the half angle formula, which means that cosine alpha over 2 times sine of alpha over 2 is simply sine 2 sine alpha. And this is 1/2 cosine gamma b sub 0 t. The 2's cancel, and we get h bar over 2 sine alpha cosine of gamma b sub 0 t. We now go with and do the same calculation with S sub y, which is the same. And now we put the S sub y matrix in, which is h bar over 2, 0 minus I, 0. And we apply it to chi of t. So we get h bar over 2, and then we have the transpose of chi of t here. And on the right side, we get a vector, a column vector, which is minus I alpha over 2 e to the minus I gamma b sub 0 t over 2, I cosine alpha over 2 e to the I gamma b sub 0 t over 2. Take the product of these two, so it would be a cosine times a sine, and the sine times the cosine, but now we have a minus I here and a plus I in the second term. So we again can factor out the cosine alpha, sine alpha. But now we get, in this term, we get minus I e to the minus I gamma b sub 0 t plus e to the I e to the I gamma b sub 0 t. But this then is just related to 1/2 sine of gamma b sub 0 t. And again, this is just going to be the sine of alpha. So we get now, with a minus sign pulled out, we get minus h bar over 2, because we have two i's and we get a minus sign out of those, minus 8 sine alpha sine gamma b sub 0 t. So we have now s of x, expectation value of s of x. We have the expectation value of s sub y. Now we have to take the expectation value of s sub z. So we do the same thing, but now we put the s sub z matrix in, which is h bar over 2, 1, 0, 0, minus 1. Now this is a little bit more straightforward because this will not flip any of the elements of this vector. It would just multiply the top one by 1 and the bottom one by minus 1. And so we get h bar over 2, cosine of alpha over 2 e to the minus I gamma b sub 0 t over 2. And then we have sine alpha over 2 e to the plus I gamma b sub 0 t over 2. And in here we have a vector that is cosine, a column vector, which is cosine alpha over 2 e to the I gamma b sub 0 t over 2, and minus sine alpha over 2 e to the minus I gamma b sub 0 t over 2. Now when we multiply these, the exponential terms, the complex exponential terms, cancel to 1, and we have cosine alpha over 2 squared plus minus sine squared of alpha over 2. And so we get cosine squared of alpha over 2 minus sine squared of alpha over 2, all times h bar over 2. But this again can be rewritten as cosine alpha. So we finally get, for s sub z expectation value, we get h bar over 2 times the cosine of alpha. Therefore, the three components that we've measured or calculated are h bar over 2 sine alpha cosine of gamma b sub 0 t. For sy, we have minus h bar over 2 sine alpha sine of gamma b sub 0 t. And for s sub z, we have h bar over 2 cosine of alpha. So, s, the time dependence, is only in sx and sy. S sub z is constant, right? It's whatever cosine, whatever alpha is, this is going to be a constant value. So you can imagine that this means that the z component projected, the dipole moment projected onto the z-axis is always fixed, h bar over 2 times cosine alpha. However, these two terms will rotate around the z-axis, one with a cosine behavior and the other one with a minus sine behavior. So this means that s is precessing, the spin precesses about the z-axis at a fixed angle alpha, such that s sub z expectation value is constant and the other two are constantly changing. Well, what does that look like? It looks like something like this. Alpha is the angle from the z-axis, and so s times the cosine of alpha is merely the projection of s onto the z-axis. The rotation frequency omega is just gamma times b sub 0, and the y component looks like a sine, so it's rotating around this. The x component looks like a cosine, so time equals 0 starts here, and then you're rotating in this direction. Because this is negative, you're rotating in the opposite direction, so the clockwise direction in this case. And sx and sy are constantly changing. The precession frequency, gamma b sub 0, is called the Larmor frequency.